Hi, today we're going to work through some more of the trends of the periodic table. You know the drill at this point. Feel free to pause if you want to answer these for yourself. I do suggest it. Link to a reference table above our heads. My head, at least. What occurs with the atomic number of the elements? What occurs as the atomic number of period 2 increases? So we're going from left to right. Nuclear charge decreases. Nope, that's not true. A nuclear charge decreases. Nope, it increases. And the covalent radius, also known as the atomic radius, decreases. Yep, small atoms over here, larger atoms over here. When an atom of lithium loses electrons, we lose electrons, so we're going to become a positive ion. And when that happens, the radius gets smaller. So to get started for today, the next trend, as it said on the title, was ionization energy. You know from your graphing activity that the ionization energy of alkali metals of any given group decreases as you move from top to bottom on the periodic table. The ionization energy will go up as you go from left to right, from metals to nonmetals. So we're going to delve into why, but I thought it might be nice to get just a frame of reference for how this looks practically.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal's surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal.
All right. Okay. So there's the one thing I wanted to call attention to in that chemical equation, if you grabbed it super quickly, was that the sodium was going from no charge to a positive charge. So some conservation of matter says you become that way by losing an electron, and that's what I wanted to talk about, to not lose sight of. So in general, that I didn't define this because we've already talked about it, the ionization energy is the amount of energy required to remove the outermost electron from your atom. We're going to define it as ionization energy, but a lot of people call it the first ionization energy. It's kind of understood that if I say it, I mean the first one. And they are numbered having to do with which electrons are being removed, like first ionization energy, second ionization energy. You can remove more than one electron. But the idea is just to draw a quick picture of hydrogen. We know that if you absorb energy, the electron moves to a higher energy level, right? You get that excited state. So we're talking about a similar process, but we're talking about absorbing more energy. Like if you gave a lot of energy to this electron, hypothetically, it's just going to leave the atom completely, leaving behind just, a positive ion. In the case of hydrogen, that's just your nucleus. So in both of these cases, we're targeting this one electron that's way on the outside. This one being lithium, the same as before. This is rubidium. We saw both of those in the video. You saw that there was a reaction, and you saw that it was more vigorous with rubidium. So we can kind of draw that conclusion there, at least in this case, that a lower ionization energy yields more reaction. Okay, so that's our relationship here. Lower ionization energy, more vigorous reaction, bigger reaction. And I think that's kind of hard to connect together because we've got this energy and the reaction, how reactive, and considering all that. But in general, I just want to talk about the one step, not the reaction with water or air, where we remove the electron. So I want to make sense of these numbers. Seemingly a lower amount of energy is needed to remove an electron from rubidium than from lithium. In other words, it's less pull needed to get the electron out. When you see these numbers, it's kind of like how much you have to pay in to get out your product. So if we're going to talk about things like effective nuclear charge and size, we know this is a small radius. And from before, our effective nuclear charge is a +1. And for rubidium, this is a relatively large radius, and the effective charge is still a +1. So the effective nuclear charges on the valence shell, this is for the valence shell, in both cases are the same, so the radius seems to matter here. Larger electron means lower number. So I guess what you can kind of draw as a conclusion from this is that distance matters. The farther away the electron is, that yields an easier, it's less energy needed to remove the electron. So we can still tie that back to, it's far away because there are more occupied energy shells. And so that kind of makes it more space, and that's easier to remove. So in general, it seems like this is a comparison down a group. Down the group, that's a decrease, and that's why. As we go across a period, let's just remind ourselves from the numbers before. We've got +2, +7, and +4 as our effective nuclear charges. In this case, we've got two things to consider. We can say the number of shells, and we can say the size. Beryllium is relatively, we're just going to label them relatively, large. The fluorine is relatively small, and the carbon is relatively medium size. So if we were to rank them, the largest would be beryllium, the smallest would be fluorine. Well, we said before that size matters, and that the closer the electron is to the nucleus, the number seems to go up. And I see that here, but there's a much larger difference. It's almost double the amount of ionization energy to remove an electron from fluorine than from beryllium. So I think the other thing we also probably should focus on is this effective nuclear charge. So the two things that seem to matter is both size and effective nuclear charge. So small atom, but also larger effective nuclear charge causes stronger pull on the electrons, which would then yield a high ionization energy. So I guess if you wanted to look at it this way, you would predict that based on this ionization energy, that beryllium would be more reactive potentially than carbon when it comes to removing electrons. So that's also a good idea to keep in mind to tie it back to what we were seeing before. So our general trend, just to echo to what we saw before, this is a picture from your reference table, is that the ionization energy increases as you go from left to right across a group, and it decreases as you move from top to bottom. This means that we have lower ionization energies here, which, on the lower left-hand side of your periodic table, you have metals, and we have higher ionization energies here, which that would be mostly associated with nonmetals. There are some diagonal trends if you follow that, bottom left to upper right, just like before, but it's really hard to draw any sort of ionization energy trends in the, upper left to lower right diagonal path. Thanks for watching.